Hello and welcome to the ASC video series. My name is Dr. Sean Perry. This is Introduction to Statistics STA 2023. We're looking at problems from Chapter 9 concerning hypothesis testing. Before we begin, let's talk about the general premise of hypothesis testing. Someone is going to tell you a fact, some mean, some average value that they tell me is true. And I want to know if that's likely to be true or unlikely to be true. So what we do is we take a sample, presuming that this is true. We should, for our sampling distribution, wind up with a normal curve around mu. And what we can do is we can specify a certain probability in the tails. And this is the probability that a sample that we take is going to wind up that far away from the mean, if this mean is true. And what we're going to do is we're going to have this value, which we'll call alpha, be something very small. And what we are saying is that if we were to take a sample and we found a value out there in this area, this far away from the mean, well, that's very unlikely to be true. And so the statement that the mean is truly centered where we were told it was is also unlikely to be true. So generally you proceed for a certain size n to take a sample, and we should get a mean for that sample x bar. Now, should x bar fall inside of our proposed region, well, this is something that would be common if the mean were truly this mean in blue, the mu in blue. If, on the other hand, it were to fall somewhere out in the wings, out in the far away region, well, then we are unlikely to agree that mu is very likely to be the mu that's been given in blue. So to formalize this, they'll call this proposed mu mu naught. And there will be a given null hypothesis. In this case, I've drawn what's called a two-tailed test. We would care if the mean that we found was very far away, either above or below the given mean. So we, in our null hypothesis, presume that the true mean is this value that we were given. And the alternative to that is that it is not the value that we were given. Now, in order to arrive at this conclusion, we can either do one of two things. We can either define a z or a t-score that is going to go here and be our critical statistic, our line in the sand. If you cross this line, we are going to decide that the null hypothesis is unlikely to be true in favor of the alternative hypothesis. And so we might propose for, let's call these guys x1, x bar 1, and x bar 2. We might derive z-scores for these. And notice that this z-score is closer to 0 in the red and farther away in the orange. In the case of z1, you would fail to reject the null hypothesis. We can't say that it is unlikely to be true that the mean is truly this value mu naught. In the case of z2, we could say it is unlikely for the mean to truly be this value mu naught, because we took a sample and we found something really different than that. Another way is to go directly to this area here, the area alpha, the probability that you just got a score, got an average score for your sample that was in these regions, even though it's true that mu would be equal to mu naught in that case. So if we wanted to, we could compare the areas instead and arrive at the same conclusion. Notice that the area I've shaded just now in red is much bigger than that corresponding tailed area in the right-hand side. It's larger, and so we would arrive in that conclusion. So we would call this the p-value. I'll call it p1. Actually, technically, this is just half the p-value, because this wing over here is half of alpha. So I'll be very specific what I mean by this area. In the case of a one-tailed test, which we'll look at later, it would just be the tailed area. But here, this is P1, and specifically it's half of P1. Let's look at this orange area, this tiny little bit for X2 corresponding to Z2. Well, this is, we'll call it P2. And notice how much smaller that is than the alpha over 2, which is over here, right? To refresh, this tailed area here was our alpha, and it's much bigger than P2 over 2, right? This right here is our alpha over 2. And that's the reason for the over 2 part. That's not the full alpha. So we could multiply them all by 2 and compare P1 directly to alpha. We'll see this in the problems to follow. Take a quick glance at the formulas for this chapter. Essentially, they are about calculating those test statistics in the case that we are talking about sigma known, sigma unknown. We use t-values then, and for proportions corresponding to large samples. Suffice it to say, if they're going to talk about a proportion, they're going to give you a large enough sample. And then we'll use these formulas instead to calculate our test statistic and our standard deviation of the sampling distribution. So now let's read a problem from the homework. This one says, a car battery manufacturer claims that its car batteries last at least 4 years on average under normal operating conditions. However, for many consumers, they've experienced battery failure well before 4 years. A consumer advocacy group decided to investigate the company to determine if the company's claim about the average lifespan of their car batteries is exaggerated and misleading. A random sample of 41 batteries was collected and tested by the consumer advocacy group, and the mean lifespan was found to be 3.79 years. Use the critical value method to test the hypothesis that the mean lifespan of this brand of car battery is less than 4 years, using a significance level of 1%. Assume that the standard deviation of the lifespan of all batteries produced by this company is known to be 0.41 years. So let's begin at the bottom here. It says that the standard deviation is known. This tells me that we have sigma, and sigma is equal to 0.41. We are testing using a significance level of 1%. That is our alpha value. It's the probability that we would reject a true null hypothesis, also known as making a type 1 error or convicting an innocent man. What are the hypotheses that we're testing? Well, the alternative hypothesis is that the true mean is actually less than the mean that they gave us, which is 4 years. 4 is here playing the role of mu naught that I mentioned before. And therefore, our null hypothesis is the complement of that. Above it said that this random sample of 41 batteries, so therefore we have n, it's 41, was tested by the group, and they found a mean lifespan for their sample of 3.79. So we have x bar equal to 3.79. And this is all the information we need to begin looking at this problem. So here I've copied the problem. Let's take a sketch. What has been claimed is that the mean is truly 4, and we are testing the hypothesis that it is in fact less than 4. So we take our alpha value, our area, and we put that all on the left-hand side here. So in other words, this area here is the full 1%. Now in the problem, they ask us to use the critical value method to evaluate this problem. And the critical value we could find already. There's going to be a certain z-score that goes here, which marks off 0.01 in the tail. So I would say we could just do the inverse norm here of 0.01. Alternatively, you could go to your z-table and look in the area section for the number closest to 1%. We go second, distor, inverse norm, and we type our left-handed area. And this gives us negative 2.326. Now let's take a look at the test statistic. So the test statistic is the z-score derived from our mean. So how do we do that derivation? It's the usual way. That is to say, it's really no different than last chapter. Notice that sigma of x bar is just given by sigma divided by the square root of n. And so what I will generally do while calculating my z-score is load that entirely into the calculator. So just to be clear, that's x minus mu up top, or 3.79 minus 4, divided by 0.41 itself divided by the square root of 41. Again, why do I load this all into the calculator? Because the more you round, the more error you accumulate. This is the most precise answer. So you have negative 3.2796. I'll round this to negative 3.28. Now, if this is a z-score, we can plot this against our z-critical. The mean, of course, has z-score of 0. So this is going to be on the left as well and more negative than our z-critical. So we would plot it somewhere over here. Now that is the weird zone. This is the rejection region. If you find something far from your mean, it's unlikely that that mean is true. So in this case, we would reject the null hypothesis. Let's go through the answers and see how we did. So we got the correct statement of the null and alternative. It is indeed left-tailed because it's less than here. And because we knew sigma, we should use a z-score. And so, yep, we got the correct answers up to rounding for the test statistic and the critical z-score. We notice that since the test statistic is farther left than the critical z-score, that we would reject the null hypothesis. In fact, the mean lifespan is likely less than 4 years, and the company's claim is likely false. All right, let's take a look at another problem from the homework. This one says, COVID-19, novel coronavirus, took the world by surprise in late 2019. By early 2020, nearly all countries worldwide were affected. Early reports from the U.S. Center for Disease Control and Prevention, the CDC, estimated that approximately 32% of those infected with coronavirus were asymptomatic, showed no symptoms of the virus. The rate of asymptomatic infections is important since such people can unwittingly spread the virus to those around them. Suppose that 30% of a recent sample of 514 infected individuals were found to be asymptomatic. Using a significance level of 5%, test the hypothesis that the proportion of all people infected with the coronavirus and are asymptomatic is different from 32%. Use the p-value method. So let's start to digest this problem. We know that we're going to be conducting a test of a proportion. So we're going to use the proportion formulas for our test statistic. They have asked that we use a 5% significance level. So that's going to give us alpha equal to 0.05. They have told us that the CDC said, so this is going to give us our null hypothesis, our test, our claim to test, that the mean was actually going to be equal to 32%. The alternative hypothesis, on the other hand, says that it is different from 32%. We were told that they take a sample of 514 individuals, and in this sample, the proportion P, which is the number of infected individuals divided by N, they just told us straight away that that was equal to 30%. Now, 30% is less than 32%, but we want to know if that is enough less. We want to know if that is different enough to say that the true parameter is likely not 32%. So let's get a quick sketch going of this problem. We were given a mean to check that that was 32%. And our sampling distribution would, if this is true, be centered on this mean. Now, we are testing with an alpha value of 0.05. That's going to be the area contained in both of these tails. So if there's 0.05 split between two tails, then each one of these is 0.025. So this total area adds up to 5%, but each of these is in half, 2.5%. And what we want to do is check to see if the value P is equal to 30, and this should in fact be P hat here. That's the sample proportion. And really, while I'm being technically correct, all of these mu's should be P's. So let me switch that. And this is just a name for the population parameter when we're talking about a proportion. Please don't get that confused with the P value, which is different and is the area that we're going to get associated with our test statistic. So first, let's calculate our test statistic. So notice that we have a large sample and we're dealing with a proportion, so we're going to be using the z-score. And as usual, z-score is the difference between our samples value minus the population parameter divided by the standard deviation of the sampling distribution. And we can check on our formula sheet that the standard deviation of the sampling distribution is given by the square root of PQ over N. Notice this is different from the previous chapter where it was P hat Q hat over N. That's because we are looking at a hypothetical distribution centered at P, while before we were centering our confidence interval on P hat. So because we're assuming that this is at center P, you have this following change in your standard deviation formula. Again, just for completeness, Q is equal to 1 minus P. So you know me, I'll plug this whole thing into my calculator. We have 0.3 minus 0.32 in the numerator, so I put that in parentheses, and I divide that by the following that I'm also going to put in parentheses. This is the square root of 0.3 times 1 minus 0.3 divided by N, as so. Typing this into our handy-dandy calculator, we get the following: negative 9.89 and so on. Now, this test statistic is associated with a certain left-tailed area. To see what that left-tailed area is, and therefore see how that compares to the alpha area given, I'm going to get normal CDF and go from some very large negative number like negative 10 up to negative 0.989 and so on. If you want to include more decimals there, feel free. It just gets you a more accurate answer. So you could take advantage of your calculator's ability to store things as a variable, store this as Z, and then we could go into second distor, normal CDF, and we'll keep this low number here, although, to be honest, minus 10 will work when we're talking about Z-scores. And then we could put exactly that number in right here, or just type negative 0.989, it really doesn't matter. You'll get at least as accurate an answer as the table would give you. And so we get the following area, 0.161 and so on, or roughly 16%. So compared to this 2.5%, 16% is going to be something quite a bit bigger, right? So this value that we've just calculated here is our 0.161 and so on that we just calculated with normal CDF. Now, as I mentioned in the intro, that's not P. That is 1/2 of the P value. This is because we're comparing it here to 1/2 of alpha. To get the actual P value then, all we have to do is take this number and multiply it by 2. So to give a new line, what is 2 times that? It will be our P value, and we calculate. And now we could compare this directly to alpha, who is given for this problem as 5%. The point of the p-value is to compare it directly to alpha. Now we notice that alpha is less than p, and this means that we are much closer, as you can see in the illustration, to the mean. We're not out here in the weird zone, we're over here near our mean. So this is something that we would get if the population parameter, p, different p, was actually still equal to 32% as they claimed, right? We would expect to find something close. Okay, so let's see how we did. So, right, because they're looking for a difference from 32%, we use not equal to and equal for our null hypothesis. Not equal to means we care if it's too little or too big, and so this is a two-tailed test. We get a Z distribution that we should use because the sample size is large and we're dealing with proportions. The test statistic, as we calculated, was 0.99 approximately if we round, and the p-value wound up being 32.17%. If we had taken this value out to several more decimal places, we would get the correct values there. And so that does not provide sufficient evidence to reject the null hypothesis. We in fact found a fairly normal result if the null hypothesis is in fact true. So what we say is that the data doesn't tell us that we could reject it. That's how we say that it is likely true. Notice that as the last statement in the line here. It says, and thus we conclude that the proportion of people that are infected with coronavirus and are asymptomatic is likely equal to 0.32%, because that was the null hypothesis, and we failed to contradict that. Okay, I hope this has been helpful for you, and good luck with your studies.